Swayam Prabha. Digital India. Educated India.
That's what I am saying. So, first try to figure out what this inequality is saying. It is saying that a random variable x, so this is your A, probability that this random variable takes values in here is, I can put an upper bound in terms of the expectation, which is the first moment of the random variable, divided by A, right. So, the smaller A is, the right hand side of this inequality goes up, makes sense, right, because it is going to have more and more value. So, you are going to have, you are adding more probability mass. So, it is making sense, right. Let us now try to prove it. Okay, so, this has a trick. What I do is, so what I do is I will now bring in a 0 1 random variable, which is kind of more easy to handle. So, if you look into this area, for this area x by A is surely greater than 1, right. Because your x is in this zone, greater than A. So, x by A is going to be more than 1, and for this zone your x by A is kind of less than 1. Okay. Now, I will use this fact that x is greater than or equal to 0. Yeah. It is a new variable that I am defining. X is a random variable. Based on that, I am defining a new random variable, right. So, if x, this random variable x is taking values less than A, the random variable I is going to take the value 0. If it is going to take, x is going to take more than A, then the random variable I is take the value of 1. So, it is a derived random variable. Which one? So, I want to write an inequality or an equality involving I and x by A. Which one of these holds? Yeah, go ahead. Less than or equal to, right. So, the first one holds, good. Why? Right, else it is 0, fine. X is always positive, good. So, this is less than or equal to. So, once you do this, the rest is easy. Achha, I is a 0 1 random variable, right. we know how to handle it. Is nothing but probability of I equals to 1. Done? You are okay with this step? This we did earlier. And probability of I equals to 1 is nothing but probability of x greater than a. That is what I wanted on the left side, right? So, I have reduced probability of x greater than equal to a in terms of expectation of I. So, the rest is easy. I have this inequality, right? So, I can take expectation on both sides, because expectation is kind of a summing argument, right? It sums. So, expectation of I would be less than equals to expectation of x by a. So, because of that, so maybe I write it as 1. So, this is now less than expectation of x by a because of 1. A is a constant. Done. Okay. Now, let us look at an example. I will use this running example as I go along, doing Chebyshev, then doing Chernoff. So, the example is this simple, this coin tossing example. You flip an unbiased coin whose successive outcomes are independent, and you want to figure out now what is the expectation of the number of heads. Fair coin n by 2, right, because you are flipping it n times. So, your expectation is n by 2. I am now interested in the tail of this, right. So, say for example, I want to know what is the probability that x takes a value say greater than equal to 3n by 4. So, some fraction of n, because you are repeating the experiment n times, n by 2 is your expectation that you know. So, you are interested in figuring out how away you are from your expectation. So, coin unbiased independent flips, you have n flips. So, if x is the random variable that catches the number of heads, then you know that your expectation is n by 2. I am now say interested in how much. So, how much this should be according to Markov's inequality? Quickly do it. So, your a here in here is 3n by 4. It is? So, this is equals to Now pause here a little for a little moment and try to figure out whether Markov's inequality is telling you reasonable things. Think of this, you increase this fraction from 3 by 4 to say something more, 5 by 6, 7 by 8. What you would get on this side, on this right side, is again a constant. So constant probability is kind of a high probability. So that means Markov's inequality is not telling you much. What I wanted to say that the random variable is concentrated around its mean, around its expectation. But in here you see that what it is telling you is that you go say a constant distance, a constant fraction away from the expectation, the probability is not falling much, it is a constant. So I want the probability to rapidly fall, 1 by n. That would be a very low probability. Fine. So as Markov's inequality is not telling me much, let us see if we can develop a little bit more advanced tail inequality. In line is something called Chebyshev's inequality. So did you get the feel of what is happening? No. I think you repeat what? Okay. As I said, it's like our, we say that a random variable behaves nicely if all the values of the random variable are kind of concentrated around its mean. If it is so, then figuring out the expectation tells you a lot about that distribution. Say all the values that the random variable takes is around plus minus delta of the expectation. If that is the case, then you know about this distribution, right? So that means if that is the case, then just figuring out the expectation, which is the first moment, tells you about this distribution. Now if your inequality, the mathematical tool at your disposal, is not that strong enough to make such a strong statement, then you would make a weak statement like this, that you know that this experiment, for this experiment, your intuition tells you that for all times I repeat this experiment, the value is going to stay close to n by 2, right, if it is an unbiased coin and the trials are independent. But what I see is if I vary this 3 by 4 and take this fraction very close to 1, you would get there also a constant, right. So vary this to 3 by 4 to say 5 by 6, 7 by 8, 9 by 10, you keep getting close to 1, what will happen? Just change that probability, right, it will get a little bigger. And finally you might get 1, and then this is telling you nothing, right. So if you say that a probability of a random variable taking a value is equals to 1, you are saying almost nothing. That is not a mathematically significant statement, right, because you know that this random variable takes a whole range of values between 1 to n. So did you get the point now, right? So my final goal is to say that the random variable is concentrated around its mean. Obviously this would be a probabilistic statement, so I want to push that probability high. So that means here it should be low, that x away from the expectation should have a low probability. That means x around its expectation should have a high probability. So did you now get it yourself? Any more questions? Well, getting into Chebyshevs, Chebyshev is nothing but Markov in a disguised form. I don't allow 0, I think, for any a greater than 0. First look at this. So, the set of random variables satisfying this inequality. This is a set. So, I look at all values of this random variable, subtract it from its expectation and say that this mod of this quantity is greater than or equal to a. So, this expression gives you a set of values that this random variable will take, right. So, this is a set. Agree to that? Fine. So, now I can take probability over it. So, this is now making perfect sense. Chebyshev's inequality does tell you that this is variance of x by a square. So, variance is second moment. For random variables for which you cannot compute the second moment, Chebyshev is of no use. Then you have to fall back on Markov. Let us now prove it. So, just take 2 or 3 minutes and try to look at the same experiment of n unbiased independent throws of a coin and see if you can plug in that to Chebyshev. Quick, do it. Each throw is independent, same probability, unbiased coin, probability is half. See if you can apply Chebyshev's to that. The problem setting remains the same as the Markov's example. Just check if you can apply Chebyshev's. We will prove this result a little bit later. Assuming that this is true, apply it. So, take the same example, try to apply Chebyshev's and see what you get. What is the random variable x? The number of heads. I have to get the variance of x. Expectation is n by 2 that I know. What is variance? How much are you getting? Or you can't deduce? What is x? Random variable representing the number of heads. X takes value in the range 0 to n. We already know what is expectation of x. Expectation of x is unbiased coin, n throws, n by 2. I want to know the variance of x. So, a thumb rule in probability is whenever you are handling a random variable that it's kind of feeling complex for you, break it down into 0, 1 random variables, right. So, how can I see x? Right, because xi is the ith throw. So, xi is equals to 1 0. So, 1 if it is a head, 0 otherwise. So, what is probability of xi equals to 1? This is equals to, this is equals to half, because it is an unbiased coin. What is expectation of xi? Half, because expectation of a 0 1 random variable is same as its probability xi equals to 1. So, this is half. Linearity of expectation, because you are adding n such random variables, this is n by 2, right, fine. So far so good. Okay. Now see, my final goal is to find this variance. That means this variance, right? But what I know, xi's are independent, right? Because successive throws were independent. So, this can be written as the sum of individual variances. So, if I can figure out variance of xi, I am done. What is variance of xi? This is expectation of xi square minus now see, xi is a 0 1 random variable. So, what can I say about xi square? It is also a 0 1 random variable, because when xi takes the value 0, xi square is going to take the value 0. When xi takes the value 1, xi square is going to take the value 1. Right? So, what is each variance xi going to be? E of xi is what? Half. So, this is going to be 1 by 4. Good. So what is now variance of x? N by 4, right? It's n by n times sum. Okay, now look into Chebyshev's formula. This is variance of x by a square. Okay. Now I want to kind of do the same thing, x greater than equal to 3n by 4. But Chebyshev is not exactly in that form, right? Markov was in a situation where I knew nothing, but in Chebyshev I obviously know expectations because I have computed the variance. So Chebyshev is asking me to take the deviation of the random variable away from its expectation. So this I want an upper bound on this, but exactly Chebyshev is not in this form. So I have to somehow extract the Chebyshev form out of this thing, right? Okay. Now if x is greater than equals to 3n by 4, then I can perfectly do this. So I can also do this here, right? The set of all values that the random variable x is going to take satisfying this inequality. You agree to this? So what is this right side? Sure. So this is n by 4, right? This is still not in the form of Chebyshev. But what if, now let me go to the next page. Till now we have got x minus n by 2 greater than equal to n by 4. What if, now see, I mean, instead of n by 2 I can write expectation here, right? So perfect, x minus ex done greater than equal to n by 4. This is equal to, fine. Now what if I write the set of values this random variable will take for this case and this case, which is kind of the superset. The second one is telling you that it is allowing more values of the random variable. So your set is bigger. And yesterday, while discussing the axioms, we had made a proof that if A is a subset of B, then probability of B is always greater than probability of A. So I apply that here to get this inequality. Now this is perfectly in Chebyshev form. So Chebyshev tells you variance of x by what? A square. So compare this with Markov. What was Markov telling you? Probability x greater than equals to 3n by 4 was what? Can you just tell me that value? 2 by 3. What is Chebyshev telling you? You understand the reduction? Now it is no longer a constant. It is saying the more you increase n, the more this value would decrease. So that means more you repeat this experiment, x is always going to take values very close to the expectation, because that probability is going to go down as you increase n. Now see the dramatic improvement just the moment I bring in second moments. So I will stop this session with the proof of Chebyshev. So we have seen an application of Chebyshev. So we have compared Markov and Chebyshev. So I need to convince you that this inequality is true. Now as I said, this is nothing but Markov's applied in a nice way. Okay. So I need to prove that variance of x by a square. The set of values of x satisfying these two are the same. So I can write this What is the above one? This is nothing but variance of x by a square. That is the proof. Okay. So we will break here. What remains is to do Charnov. So in the next half, which was supposed to be min cut, I would first do Charnov and then I will shift to showing you an example in graph theory where this theory that we have studied for the last 2 lectures would be applied.